All right, this video is for my BC Calculus class because we lost a day. And since we lost a day, they didn't get a cute little teach piece on the Fundamental Theorem of Calculus. So I thought that I would do a quick little teach piece on the Fundamental Theorem of Calculus, and I won't take any more than 10 minutes. So there. The Fundamental Theorem of Calculus comes in two parts. Part 1 is the part that gets the short end of the stick usually, because it's not very useful. And what it says is that if you take a derivative with respect to x of an integral function, and the integral function runs from some number to that variable x, and you're integrating some function, f of t dt, and we should note that t is different than x, t is a dummy variable, that the derivative of that integral function is f of x itself. I should note that we put this x right in there. And so when we, let's see, we'll do some practice. So when we do things like take the derivative with respect to x of the integral from 3 to x of t squared dt, that this x substitutes right in there, and we get x squared. When we change things up, take an integral from 4 to x squared of cosine t dt. I should pause to make sure we understand what that means. What that means is that somewhere off on some other page is a function called cosine t. This function exists on some other page that we're not talking about. Maybe I'll draw it. Here's cosine t. La 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 la. Oh, it's terrible. Redo that, Mr. Ritter. Redo that. Okay, fine. So here's cosine t, and la 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 la. That's better. And 4 is right about here. So when I talk about the integral from 4 to x squared of cosine t dt, you have to imagine this function where if x is 3, then I take all the area from 4 to 9, all that integral, and add it up, and that is the value at 3. And so what this integral function does is it keeps track of all of those integral values all the way up and down the number line. If I take the derivative of that function, if I were to plot it and take the derivative, then x squared goes right in there. We get cosine of x squared. But wait, Mr. Ritter, chain rule says that if I'm using something that isn't x up here, I have to multiply by its derivative, and that's absolutely true. That is absolutely true. So that's a quick little refresher for you guys. It does help. Let's see. We'll try another example. Let's take the limit as x approaches 0 of the integral from 0 to x of e to the t dt over x. And to be quite honest, the College Board has a boy crush on problems like this because it makes students remember two things. It makes them remember the Fundamental Theorem of Calculus, and it makes them remember a thing called L'Hopital's rule. And it makes them remember a thing called L'Hopital's rule because to do this, let's see, can't we just substitute 0? If we substitute 0, you've got an integral from 0 to 0. And we all know what an integral from 0 to 0 is. That's 0. And the denominator gets closer and closer to 0. And we have a little theorem in my class that says that 0 over 0 is weird, and so we can't do that. So how do we respond? Well, we use L'Hopital's rule. And by L'Hopital's rule, what we do is we say, look, I'm going to take the derivative of the numerator and the derivative of the denominator and try again. And if I can get the blue limit to work, then the black limit works and has the same value. So the derivative of the denominator is, of course, 1. The derivative of the numerator is the derivative of an integral function from a number to x. And so we take that x and throw it right in there. And this is a limit we know how to do. The top approach is 1. The bottom is 1. And so that limit value is 1. So there's your Fundamental Theorem of Calculus Part 1. The fundamental theorem part 2 is much sexier because that's the one that's got all the applications, and that's the one with which you are probably familiar. And that's the one that says if you take the integral, the definite integral from a to b of f of x dx, that's equal to capital F at b minus capital F at a, where capital F prime is the same as little f. This is the thing that helps us find the area under a curve. This is the thing that helps us keep track of area accumulation. This is the thing where if I know how to find an antiderivative, I can find any definite integral that I choose. This is the thing with which we are most familiar. I would like to do one of these jobbies. Let f prime of x, capital F prime, equal natural log x cubed over x if capital F at 1 is 3, find capital F at 9. And the use of capital F is intentional here. It is intentional here. So what do I want to do? Gotta think this one through, folks. What do I want to do? I want to get from f of 1 to f of 9, and that's doable if I can keep track of all the rates of change from 1 to 9. It would be glorious if I could do that. If I could integrate natural log x cubed over x from 1 to 9, if I could do that, if I integrate capital F prime, then the fundamental theorem tells me that that's capital F at 9 minus capital F at 1. And since I already know capital F at 1, I'm in good shape. And I'm in good shape because the machine will give this to me. The machine will figure that out. So once I get that out of a machine, I just add f of 1 and I'm done. So we'll go do that. We'll bring up the machine. I'm sure you're doing it at home where you're watching this. I am positive of it, even as I am doing it for you. We'll do a math 9. That's an f and int. And we're going to integrate natural log of x, quantity cubed divided by x with respect to x from 1 to 9. The calculator is going to do that for us, so we know that 5.82690 whatever is equal to capital F of 9 minus 3. And so capital F of 9, we just add 3, and we round to 3 decimal places. And we've got it. Remember that the fundamental theorem is one of those things that helps us keep track of area accumulation. By integrating, we keep track of all of the rates of change from 1 to 9. If I can do one more, I think I can without going too long on time. Consider the following. You got some crazy graph here, and this is -5, -2, and this is -3, +2, that's -4, 0, and this comes along to 0, 1, and this will be a nice half circle touching at +1 here and going up to 2, 1, and then this goes like so down to 4, -1, that hitting at x equals 3. This is going to be some function f. And what we'll do is we're going to let g of x equal the integral from -3 to x of f of t dt. And we're going to find some things. We're going to find g of 0 and g prime of 0. We're going to say, where does g have a max? and we're going to say, where are the inflection points of G? Just a quick little teach piece here. This would be a nice, probably 7-point question. I'll probably have to throw in one more part to get a 9-pointer. So G of 0. G of 0 is the integral from -3 to 0 of f of t dt. It is this area. And that's the area of a trapezoid. That's 1/2 times the height times the sum of the bases. Well, the height is this horizontal distance, that's 3. And the sum of the bases, well, the bases have lengths of 2 and 1. That's 9/2. That's the kind of thing I can expect you to do on test day. G prime of 0 is the derivative of an integral function. And the derivative of that integral function is f of x. And f of 0 is 1. So we can pick that up right from the picture. We can't talk about G double prime of 0 because that would mean we'd have to find f prime of 0, and f prime of 0 is not going to exist. There's a cusp there, a corner. So where does G have a max? So let's consider a G prime chart, shall we? There are several places where G is going to be 0. Several places where G prime is going to be 0, and the places where G prime is going to be 0 are going to be the places where f is 0, and that happens at -4, and then again at 1, and then again at 3. On the left side of -4, G prime is negative, then it's 0, then it's positive for a while, then it's 0, then it's still positive, then it's 0, and then it's negative. So what does that mean about G? That means that G is decreasing, and then it's increasing, and then it's increasing again, and then it's decreasing. How do I know if I have a max? I know I have a max when I switch from increasing to decreasing. So G has a max at x equals 3, since G prime, which is f, changes from positive to negative there. And that's how you'd want to write it. You want to say that you know what G prime is, you want to connect it to the picture, and you want to say that that derivative changes from positive to negative. Where are the inflection points? Well, the inflection points, that depends on G double prime. G double prime depends on f prime. We need all those places where f prime changes. And f prime changes at -3, and then f prime changes again at +1, and then f prime changes again at 2, and that's all she wrote. From -5 to -3, G is increasing, so, well, f is increasing, so G prime is increasing, so G double prime is positive. And then f is decreasing for a while, and it's still decreasing for a while, and then it's increasing for a while, and then it's decreasing for a while. So where are inflection points? Inflection points are places where G double prime changes sign, and G double prime changes sign at x equals -3, +1, and +2, since G double prime, which is f prime, changes sign there. And that's the kind of thing that you're going to have to do for probably 7 points on test day. So I hope this gave you a quick look at the fundamental theorem. Hope it helps.